Okay, so I realized that these recordings have gotten so old, and the basic, for example, it says in the pre-lab, look at basic instructions, and 1 and 2, and they're not both there. So what we do in this lab is that we're going to test out. Hey there, hold on now. Oh, look at that. Thank you, sir. Wow. That's why I put my name on it. Anyways, oh yeah. Jake, our administrator, found my keys in the copy room. Where was I? Oh yeah. So we got Newton's law, second law. And what we're going to do is we're going to write it the way he did, because we're going to be measuring acceleration in this lab, and we're going to be varying F and M. And just you'll see why I write it out as mass there. So we're going to create our own little Atwood machine, and we have the air track. And we have a glider on there. We have a pulley, and the pulley has the photo gate. And so we label this capital M for and mass and little m. That's why I wrote it here. And so for us, the force is going to equal mg. And this is, excuse me, there's going to be a hanger. Excuse me, again, I ate my sandwich too quickly. And then you're going to be placing weights on it. So that's little m. And the mass in the equation is capital M plus little m. And once again, the capital M is the mass of the sled, and you're going to be putting weights on the sled. And you're going to do different size sleds, so you're going to be taking the mass of each one. So we're going to be doing a series of runs. And for each run, we're going to get an acceleration and a plus minus acceleration. And that you're going to get using the photo gate and the pulley. And so this is where, let's see, this is where the photo gate is. And it's a so-called smart, they call it a smart pulley. And what happens is that we know what a photo gate is, and the pulley is divided up into pi wedges. And then they have the black plastic that it's made of. And then there's openings, and the angles for these, for the, say, the dark part and the theta for the opening, they're all equal. So when this thing spins, we use the coordinate of theta for spinning. And then if we want some, we define this thing called spinning speed, rotational speed, and we call it omega, and it's radians per second. So we also can change so how do we take radians per second and turn it, we need it to be meters per second, because that's linear speed. We want to know how fast it's going on there. So we do know that we call them cycles. Every time the wheel spins around, there's 2 pi radians in one cycle, in one spin around. And we also know that for one spin around, one cycle, is 2 pi r meters. So we'll put parentheses around the units. So if we take radians per second, multiply by cycles per 2 pi radians, and then we multiply by 2 pi r meters per 1 cycle, then we see that the radians cancel out, the cycles cancel out, and the 2 pi's cancel out. And so we have, we're left with our meters per second. So if we take omega, and what's left? Just the r. So omega times r equals v in meters per second. Okay, so what you're going to do is, for the data taking itself, you're going to have a table of A and plus minus A. And what happens is the software, so you have the pulley, the photo gate, the interface box, and the software are going to combine together to show you a VT graph. And it's going to have a whole lot of points. And then you're going to take the software, and in the software, you're going to get a fit. And the software is going to give you the slope and the plus minus slope. And what is the slope of the VT graph? And hopefully you remember what that is. So your raw data is going to be, for each run, 1, 2, 3, 4, 5, possibly 6. You're going to get an A, a plus minus A, a little m, and a capital M. This used to be a little more complicated, but what you'll see ultimately in the analysis, your analysis is that you're going to make 2 graphs. And one is with constant mass, so this is going to be mg, different forces. And the slope of that is going to be 1 over m plus m. The reason is that A equals F over mass equals mg divided by m plus capital M. So in this case, we're going to hold this constant, so then that becomes the slope. And in this case, we're going to hold mg constant, and we're going to plot over here 1 over m plus Oh, sorry. Long day, I'm tired. So the pre-lab doesn't reflect that I've simplified this. The original lab write-up made this much harder. But now what I did is I added in this business of how the photo gate works and the Atwood machine concept. And so hopefully this is better. Okay, so I'm going to stop this and upload it to the YouTube playlist.